Hello everyone. Let's solve today's data code question 1986 minimum number of work sessions to finish the task. So the reason why I picked up this question is because this is a greater practice for BitMask DP. And don't worry if you never had a BitMask DP, it is actually a really easy process. And you can apply this technique to many questions when you um, want to have the arguments like hash set or list as the arguments of the DP function, and you can actually set it really efficiently. So let's go and see the question itself. So this question, so there are any task assigned to you, and the task time I represented as integer array task, and then length is n, and i's task takes task I hours to finish, and you're also given work session, and then which is um, at most session time consecutive hours, and then take a break. So the thing is, you're given like the list of tasks and and then session time, and then you can finish as much as task that can fit into the session time. And then if it exceeds or like equal to the session time, you have to take a break and you are supposed to return the minimum number. Yes, so the minimum number of work session needed to finish all the tasks following the condition above. So let's go through this example. The session time is 3. So you can, in a first session, you can finish this 1 and 2. So that takes up 3 session time. And then you can no longer have more tasks. So you kind of increment the session by 1. And then the next is this 3. And it takes up all the session time fully. So you cannot do any more tasks anymore. So again, increment the session again. And this is going to be 2. And if you think about it, you have many options. Obviously, you can finish this by session time, like by session 3. So you finish 1 at the first and then do nothing and then increments sessions. And then next is going to 2. So again, you increment the sessions and it's finally 3. So basically you're doing each task in one session, but obviously which is not efficient. So let's think of this example. And you have session time 8, so you can fit into the session time with many tasks. So let's pick up 3, and then 3, and then 2, 1, and 1. That's going to be 8 in total, and increment the sessions by 1, and finally finishing the last task, taking um, yeah, entire session, unfortunately, because you still have to have another session because um, the first session was like eating up all the entire sessions. So the last example here, so session time is 15, which is a very large number. So you can put every task into one session. So answer is answer is equal to 1. So how would you solve this question without knowing bitmask DP? So this is my simple DP function. You don't have to worry about like the speed manipulation so far. Um, but so basically I have like the visited arguments and the remaining time. So the thing is you keep maintain like how much time is remain from the session time and also the visited. Visit means the list of tasks already done, finished. So basically, yeah, you can only read this variable, not worrying about this bit manipulation. So basically, I'm saying if the task's time is smaller than remain time, you can include this task in the current session, right? And if it's not, you can increment the session time by one and, but still doing the DP, and that's going to be the result. Okay. So the only problem here is this visit usually be the list or hash set, right? Um, to avoid like, doing the old like duplicate task. I mean, the task that you already finished, you need to keep the list or hash set and then make sure that like this is unlisted, right? And if you use, and basically you cannot use the list or hash set as the, the key of hash map or like any like a list of lists like this. It's only integer that you can use as a key of like memorization. So I'm doing like this. But if this that is just a set or a list, it is impossible. I mean, it is possible, but it takes up a lot of time and it is not efficient anymore. So how do you convert this visit hash set or list into integer? That's the trick of Bitmask DP. So if you think about it, um, it's really interesting that you can represent this bit as a bit. So any number can be represented like this, 0, 0, 1, 0, 0, 1, any combination of 0 and 1, right? I hope you understand this. And how you manage the visited node, the visited index in a bit, you can simply assign 1 to the visited index. So let's make it simple. So you have 3 index. So this is 0. No, this is actually, it's a backward. So this is the first index. This is the second index. This is the last index, 3 index, third index. So when you visit, so 0 based index 2, you're going to change this from 0 to 1. Okay. And if you visit um, the middle index, that index 1, you change this 0 to 1. Okay, so that's how you maintain um, kind of the hashed the visited as an integer. So there's some tricks that you need to know. First, how would you assign 1 to specific index? And second, how would you check if it's unvisited, right? And then thus, how would you know, how would you check if you visited all of them? This is kind of the basic operation for hash set or any like this or anything. And you want to do this with the bit as well. So let's start with this one. How would you assign 1 to specific index? So this is actually done here. So the visit is the current like the bit representation of visited, and you have this weird operation here, and then this is like OR operation. So what is happening here? You're telling this is, if you remember, this is called left check. So this tells you want to shift this 1 by I. So let's say this I equal 2. In that case, you want to shift the shift 1 to by 2. So that let's say, okay, so if it's here, if it's 2, 0, 1, 2, so you're going to shift 1 to this position so that you can create this integer, right? This integer. And the thing is, because I'm doing this OR operation, so when you happen visit any nodes, any indices, it's going to be 0, 0, 0, right? I mean, it's just a zero. And if you do this OR operation, this is going to be 1, 0, 0 because OR operation takes any one um, to the result. So even if this is 1 and 0, this is going to be 1. And only both are 0, you're going to assign 0 number here. So this is how you handle assigning of 1 to the specific index. So the next is how to check if it's unlisted. So this is another trick, but it's really similar to the first operation. So look at this one. This is checking this index is already visited or not. So I'm still doing the same operation. So let's think of the same case. You already visited the second index, 0 base, and then you're trying to check it's already visited and it's actually end. What would happen here? So because this and this is 1, if if you do this operation, you get this. So what does it tells you? It tells you this index is already visited. And let's think of another example. So in this case, you are trying to find like this, the first index, I mean, yeah, 0 index space is unvisited or not. In this case, because this one is 0 here, and this one is represented 0 here, it's actually going to be 0, 0, 0. So there's no overlap between these two numbers. So that's why if this operation produces 0, that means it's unlisted. So you can do some operation based on it. So the only difference is if you do OR operation, that creates assigning. That's kind of the assigning operation. And if you do AND operation and then check if it's equal, that's checking if it's unlisted or not. Really easy. So the last thing, how do you know every indices are listed? So if you understand for now, until now, it's quite easy. So and then it's done by here, all listed. And I'm still doing the left shift. So, but in this time, I'm shifting n times. So let's say n equal 3. So it's going to be like this, right? But it is not quite like the good, I don't know, representation of all visited how do I say integers. So what you want to see, if you have the 3 indices, you want to see like this, right? You want to see all 1 because 1 means it's visited. So how do you create it? And if you can see here, I'm subtracting -1 from this 1, 0, 0, 0, 0. And what do you think would happen? Actually, so this is kind of so 1, 2, 3. So this is 8, right? And then if you subtract 1, it flips all the bit representation. So it's going to create like 1, 1, 1. It's just a bit manipulation technique. So that's how you usually generate all visited integers. And this is really useful for the base case. So you have visited, and then you have this another variable self dot all visited. And if it's equal, that means you visited all the nodes. And you can handle any base case here. So in this case, because all the indices are visited, there's no task anymore. You just can return 0. And obviously, this is the main part, caching. Now you can use the visit as a key of hash map or like list of lists or anything, and then implement this memorization really efficiently. And the next is your for looping O to N, which is the task list, and then check if it's unvisited or not. And if it's unvisited, you create the new, assigning the index, and then creating the new visited. And then if, yeah, again, the task's time is smaller than remaining time, you can do this operation within the current session. And otherwise, you're going to do this DP, but you have to increment by one because you eaten up all the sessions and then you have to move on to the next session. And then finally, find the minimum one based on this recursion and then assign to memorization and then return result. So let's run this code. Yeah, so it's pretty efficient, and it can be used in many situations. Let's see. This is, let me think. Okay, just give me a second. This is also a good example. So the thing is, you so until you reach the Baymask DB solution, you think of any DB solution, and sometimes you want to cache it. You want to cache this hash set or list as arguments of memorization. In that case, you can use Bitmask DB, but there's some tricks here. This Bitmask DBs has obviously it cannot handle many like the big numbers. It has to be 0 0 and 0 1. And if it's like a thousand of 0 1 0 1, the computer cannot represent it anymore. So when you use the Baymask DB, you have to take a close look at the constraint, especially like this part. So n is actually 1 to 14, so it's really small. That's why you can use Baymask DB. Like usually, depending on the programming language for like computer, usually 32 bits or 64 bits is the maximum. So you want to check if it's like the constraint is smaller than 32 or 64. But this is another good example. Let's see. Yeah, the constraint is really small, but you have to solve this really efficiently. So yeah, there are many techniques. In this case, you do have to do like two operation for Baymask DB, and then there are some advanced techniques based on this logic, but the whole basic idea, overall idea is still the same. And this is really powerful, and you can use it in many situations. So I highly recommend you to deeply understand this, and then yeah, try to solve a couple of questions, and then kind of try to um, ingrain this knowledge into yourself, and then apply to any question that you've never seen. Okay, so that's it for my explanation about BMS DP. I'll see you soon in the next time. Bye.